class, and title of today's lecture is Satellite Remote Sensing of Gaseous Air Pollutants. So what is air pollution? Air pollution occurs when gases and particles are introduced into the atmosphere in a way that makes it harmful to humans and plants. Basically, air pollutants are air contaminants and they have severe health implications. Air pollutants can be categorized in two categories. First is primary pollutant and second is secondary pollutant. Primary pollutants are those pollutants which are emitted directly in the atmosphere because of several activities, natural as well as anthropogenic activities like volcanic eruption, wildfire, crop residue burning, vehicular exhaust, factory, power plant, industries emission, town and home emission, shipping emission and aeroplane emission. All these activities contribute for primary pollutants concentration. The example of primary pollutants are shown here: carbon monoxide, nitric oxide, sulfur dioxide, nitrogen dioxide, particulate matter, volatile organic compounds and ammonia. These are the few primary pollutants. Few pollutants are not directly emitted in the atmosphere, and these type of air pollutants are called secondary pollutants. They are produced chemically or photochemically from the primary pollutants. The examples are shown here: sulfur dioxide, nitric acid, sulfuric acid, hydrogen peroxide, ozone, ammonium and particulate matter. Out of all these pollutants, few pollutants are very important. They have very bad health implications even for short duration exposure. These type of pollutants are called criteria air pollutants, and our government has put certain criteria on their concentration. That criteria can be seen in this particular chart. The chart shows air quality index category in 6 range: good, satisfactory, moderately polluted, poor, very poor and severe. These are 6 categories, and for each criteria air pollutant you can see concentration range, like for PM10 0 to 50, then 51 to 100, 101 to 250, 251 to 350 and so on. Like, now you can understand that if the concentration of the particular pollutant is falling between this range, then it will be good air quality. If it is falling in the, suppose for NO2 we consider the example, and here before starting that I would like to mention here that the pollutants are given in microgram per meter cube except CO, which is given in milligram per meter cube, and this is their concentration range in each category. Okay, so suppose we make measurement of NO2 for 24 hours and average concentration falls between 41 to 80, then we will say that air quality is satisfactory with respect to NO2, right? And here in bottom you can see one formula. This I is equal to I high minus I low by C high minus C low multiplied by C minus C low plus I low. Here you can understand that this formula is for the calculation of air quality index for one particular pollutant. Suppose you are making measurement for NO2 at one particular observational location and you are getting 24-hour average concentration, suppose 50 microgram per meter cube. So what will happen, that 50 micrometer will be falling between 41 and 80, right? So if in this equation, C will be the observed concentration, which is 50 microgram per meter cube. And C low and C high are the range in between which that concentration is falling. So 41 and 80 will become C low and C high respectively. And I low and I high are the index in this range. So it will be 51 and 100 respectively. So if you have measured concentration for that one particular pollutant, you can calculate using this formula air quality index for that particular pollutant, right? So if you will suppose I give an example of Delhi. So we have measurement network in Delhi, and we are making measurement of all these pollutants over Delhi, and we are calculating their daily average or 8-hour average depending upon the pollutant, and that concentration we are comparing in this table. So from here you will get, suppose NO2 you are getting satisfactory. Suppose, just 1 second. Hello. Hello. Please मेरा अपना lecture बंद. Sorry for disturbance. So suppose for NO2 it is satisfactory, the air quality is satisfactory. For ozone it is moderately polluted. For CO it is poor, and for SO2 it is very poor. And suppose PM 2.5 shows very severe, very poor or severe. Suppose severe, then severe will be the worst air quality, right? So worst air quality will be considered as the final air quality over that location. So though the NO2 may be showing satisfactory, but air quality over in Delhi will be considered in category of severe, and accordingly the health implication should be considered. Here in this particular plot, you can see absolute number of deaths from outdoor air pollution in 2016, right? And here you can see here the light color shows less number and this maroon color shows very high number. Okay, so you can see here in this plot that India and China, the death, total absolute number of death is more than 1.2 million. So we can understand that how important it is for us to measure the criteria air pollutants over our location, over our Indian region, right? Now, before going ahead, we should understand the commonly used units for air pollutants. Trace gases. Basically, this lecture will be focused on trace gases, right? So here you can see the mixing ratio. Generally, in the atmosphere, we express major gases like nitrogen and oxygen in percentage, but pollutant gases are present in very, very small amount in the atmosphere. So we do not express them in percentage. We express them in terms of mixing ratio, right? And here you can see Ni, which is number density of target gas, and N-air, number density of total air, which includes nitrogen and oxygen molecules also, including all the other molecules. So this will be, so Ci will be the mixing ratio of gas I, and Ni is the number density of that gas, and N-air is the number density of air. Okay, so we know that nitrogen and oxygen are present in very large amount in our atmosphere. So this ratio will be very small number because number density of pollutant gases are very small. So this ratio will be very small and it will be unitless quantity. There will not be any unit because in numerator and denominator both are molecules per centimeter cube. So it is a unitless quantity and very small number for pollutant gases. So it will be very small number. It can be a multiple of 10 to the power minus 6, 10 to the power minus 9 or 10 to the power of minus 12. And accordingly, it is expressed as ppmv, ppbv or pptv. Suppose this ratio is 3 into 10 to the power minus 6, we will say 3 ppmv. Now, we are going to use the satellite measurement, and satellite also measures column content. Total column content means total number of molecule present from surface to top of the atmosphere. To express this particular quantity, we use Dobson unit. What is Dobson unit? In the atmosphere, there are number of molecules from surface to top of the atmosphere. Bring all the molecules to a gas present in the atmosphere at surface at standard temperature and pressure. Bring all the molecules of the gas at the surface at standard temperature and pressure. What will happen? It will form a layer, and the thickness of this layer in millicentimeter is the column abundance of that gas in Dobson unit. Example, Suppose all the ozone molecules present in the atmosphere forms a layer of pure ozone at surface of 0.3 centimeter thickness. So it is the thickness of pure air, pure layer of that particular gas ozone, right? And we can express them it millicentimeter. So 0.3 we can write 300 millicentimeter. So we will call it 300 Dobson unit. In 1 Dobson unit, there is 2.69 into 10 to the power 16 molecules per centimeter square. Now we will understand various sources of different criteria air pollutants. So first is nitrogen dioxide. Nitrogen dioxide is not studied as independent gas. It is calculated, it is studied as NOx, NOx, which is equal to NO plus NO2, and NO is the nitric oxide and it is readily interchangeable into NO2. So NO2 which is present in the atmosphere is not only NO2 but lot of NO converted into NO2. That is why we do not consider NO2 as independent entity. We consider NOx as one particular species. Why? Here you can see a null cycle. NO, nitric oxide, reacts with ozone to produce NO2 and O2. This NO2 photodissociates at wavelength less than 420 nanometer and produces NO and O. And this O molecule, O radical, reacts with oxygen molecule to produce ozone. Now if you see, this is a null cycle. One molecule of ozone is consumed and one molecule of ozone is produced. One molecule of NO is consumed and one molecule of NO is produced. One molecule of NO2 is produced and one molecule of NO2 is consumed. So neither production nor loss. This is the null cycle. But in this process, what is happening? NO is getting converted into NO2 and NO2 is getting converted into NO. So these two species cannot be studied separately. We consider them as a single gas, NOx. So here you can see NOx emission scenario in the troposphere, and maximum amount of NOx is emitted because of fossil fuel burning. And lightning is also important source, biomass burning is also important source. And soil emission, biofuel emission, aircraft emission, and partly it is also transported from the stratosphere to the troposphere. Lightning, you must be thinking what is why lightning is a source of NO2 or NO. It is because in the lightning channel, suddenly temperature increases beyond 2000 Kelvin. And when the temperature is very high, oxygen thermolyzes and breaks into its component. And it reacts with nitrogen to produce NO and then NO2. So lightning is also an important source of NOx. Then soil is also an important source of NOx. Soil nitrification and denitrification process emits NOx in the atmosphere. Then second gas is carbon monoxide. Here the budget of tropospheric carbon monoxide is given. Here we can see fossil fuel combustion and industries and biomass burning are very important anthropogenic sources of CO. And vegetation and ocean are the average source of CO. Here range is given in teragram carbon monoxide per year. And oxidation of methane and oxidation of other hydrocarbons also a very important source of CO. But these hydrocarbons are also emitted because of biomass burning and fossil fuel combustion. Major source of CO is tropospheric oxidation by hydroxyl radical. Partly it is transported in the stratosphere and partly soil uptake. These are the loss processes of CO. Now coming to ozone. As we have seen in the previous slide, that ozone is a secondary pollutant. Ozone is not directly emitted in the atmosphere. It is produced, photochemically produced in the atmosphere from other pollutants like carbon monoxide, nitric oxide, nitrogen dioxide, and hydrocarbons. And sunlight is essential for ozone production because it is produced because of photodissociation of NO2. So we will see how it is produced. Production of ozone is initiated by ozone itself. Ozone photodissociates at wavelength less than 310 nanometer, and it produces oxygen molecule and excited state of oxygen atom, and which reacts with water vapor to produce hydroxyl radical. This hydroxyl radical is highly reactive and it reacts with n number of gases in the atmosphere. So over any urban location where sufficient amount of pollutants are present, like methane, CO, NMHCs, NMHCs stand for non-methane hydrocarbons, and NO. Then if these gases are present, then these gases are called fuel gases, and this gas is called catalytic precursor of ozone. Why? We will see. These gases react with hydroxyl radical and produce HO2 and RO2 radical. R stands for methyl and ethyl type of group. So HO2 and RO2 radical react with NO and it converts NO into NO2. And NO2 photodissociates and produces oxygen molecule and oxygen radical, and which produces further ozone. So here you can see the production cycle of ozone, and in this process NO2 gets converted into NO and NO gets converted into NO2. So these gases NO and NO2 are not consumed in the production of ozone, and so these gases are called catalytic precursor. And methane, CO, non-methane hydrocarbons, these gases are consumed in this process. They are converted into other species. So these are called fuel precursors which are consumed in this process. Partly we know that in the stratosphere there is a lot of ozone. So partly ozone is transported from the stratosphere to the troposphere, and chemical loss and dry deposition are the last processes of ozone. Now ozone problem mainly occurs when it is polluted atmosphere. In the clean atmosphere, we have seen these three equations. NO reacts with ozone and produces NO2 and O2. NO2 photodissociates and produces NO and O, and this O reacts with oxygen molecule to produce ozone. Right? So it is a null cycle, neither production nor loss of any of these species. But in polluted atmosphere, what happens? Volatile organic compound, carbon monoxide, these gases produce HO2 radical. And this HO2 radical is more reactive with NO than ozone. So NO starts reacting with HO2 radical and it produces NO2 and OH. And now NO2 photodissociates and produces ozone. So now ozone is not consumed in the process but produced. So in the polluted atmosphere, net production of ozone takes place. Now this is the chemical reactions for production mechanism of ozone. We can see this equation we have seen. Ozone produces hydroxyl radical. Hydroxyl radical reacts with carbon monoxide, produces H radical. H reacts with O2, produces HO2 radical. Then HO2 reacts with NO, produces NO2 radical. And NO2 photodissociates at wavelength less than 420 nanometer and produces NO and O. And this O reacts with oxygen molecule to produce ozone. So OH is not consumed in this process. OH is also coming back, and NO is also not consumed in this process, and NO is also coming back. Only CO is consumed in this process. A very similar set of reaction is written here for hydrocarbons, where R stands for methyl and ethyl type of group in RH. And it reacts with hydroxyl radical, produces R plus H2O. R reacts with O2, produces RO2. So this RO2 radical also contributes for ozone production because it converts NO into NO2. And again, HO2 is produced from RO, and HO2 reacts with NO, converts it to NO2. So in this process also, you will see that hydrocarbons are consumed in this process, and OH and NO, these two are not consumed in this process. This is the production mechanism of ozone. Then sulfur dioxide. Major anthropogenic sources of sulfur dioxide is combustion of coal and oil, and it is mainly emitted from power plants and industries. And major source, natural source of sulfur dioxide is volcanic eruption and oxidation of reduced sulfur compounds like dimethyl sulfide, hydrogen sulfide, carbonyl sulfide, and carbon disulfide. So now we are going to understand the monitoring of gaseous air pollutants from space. So what is the basic measurement principle for trace gases measurement from space? Which characteristic is used for the retrieval of gases in the atmosphere? The absorption property of gases are used for retrieval of gases in the atmosphere. And the absorption property is expressed by Beer-Lambert law. Suppose we have a box here, and in this box we have an absorbing gas which has number density n, having unit molecules per centimeter cube. Okay, so this is number density of absorbing gas in this box. And this particular absorbing gas absorbs intensity of radiation lambda. So wavelength which this absorbing gas absorbs is lambda. Okay, so suppose we pass this radiation having wavelength lambda through this particular box, then obviously some photons will be absorbed in this box because it is an absorbing type of gas. So, and it is very strong absorber at wavelength lambda. So some photons will be absorbed in the inside this cell, and remaining photons will be received at the other hand. So you see, I0 lambda is the incident radiation and I lambda is the transmitted radiance. So here you can see the equation which is called Beer-Lambert law, which explains the relationship between transmitted energy and incident energy. I lambda is equal to I0 lambda exponential minus sigma lambda n and L. Here, this sigma lambda is an intrinsic property of absorbing gas, and it depends on wavelength because each gas absorbs one specific wavelength. So according to that wavelength, the value of sigma is decided for that particular gas, and it is experimentally calculated, and it is a known quantity for each absorbing gas. So this sigma is used for the calculation of number density of that absorbing gas. This is called, this equation calls, we call this equation Beer-Lambert law for absorption. Now we can write this equation as I lambda is equal to I0 lambda exponential minus delta, where delta is known as optical depth and it is equal to sigma lambda, number density of absorbing gas, and L is the length of the absorbing cell. You can see L is the length of the absorbing cell. So it is there. Now this is the laboratory demonstration where there is a box, and in this box we have filled the absorbing gas. But what is happening in the atmosphere? In the atmosphere, number density is not constant like in a box. Number density continuously varies from surface to top of the atmosphere. It exponentially decays. It exponentially decreases with increasing altitude. So we can species, because in the atmosphere there is not one absorbing gas, there may be other different absorbing species at the same wavelength. So at every wavelength we have to consider all the absorbing species present in the atmosphere. Now consider another relevant information in the atmosphere, that is light will not always be incident on the surface of the earth perpendicularly, right? It is not always possible that sun is always overhead. Sun will be making any angle with the vertical line, that is called solar zenith angle and shown here by chi, right? So sunlight sometimes will come in vertical direction, sometimes it will follow slant path, right? When it is following slant path, then it will be traveling longer distance in the atmosphere before reaching to the surface. And in that case, there will be more absorber in this path, right? So we have to consider, we know what vertical depth of the atmosphere. So we convert it. So here you can see if this angle is chi, and if we make a vertical line here, then this angle will also be chi, right? This distance is L, this angle is chi, then this distance will be L by cos of chi. So generalized Beer-Lambert law for our atmosphere will be I lambda is equal to I0 lambda exponential minus delta by cos of chi, where chi is the zenith angle. And transmittance is a very important property which we will use in the retrieval of trace gases, and it is the ratio of I by I0. This I is the transmitted intensity, I0 is the incident intensity, and the ratio of the two is called transmittance, and we will use this property later. Now, before going to satellite observation, we should discuss a little bit use of Beer-Lambert law in laboratory. And it will be helpful for you to understand how Beer-Lambert law can be used for retrieval of gases. So here, one box-like instrument is shown in this figure, and you can see the schematic of this particular instrument here, right? And here you can see one UV lamp. It is ozone analyzer. It is ozone analyzer, and ozone absorbs ultraviolet radiation. So here we have used one UV lamp. Here it is an absorption cell, and here is a UV detector. And here it is a pump which sucks ambient air parcel in the absorption cell and throws out. And this happens at every 5 to 10 seconds. Right, and here you can see this is the sampling line. Sampling line means air parcel is traveling through this path as well as this path. So for 10 seconds, air parcel takes the direct path inside the absorption cell. Air parcel is sucked inside the absorption cell, and a UV lamp is used to for the I0 light passing through this absorption cell, and I intensity is measured by UV detector, right? Now for next 10 seconds, the air parcel, this is a solenoid valve. It gets connected to through this path for 10 seconds, and then it gets disconnected from this path, and for next 10 seconds it gets connected to this path. And here in this path there is a ozone scrubber which converts all the ozone present in the air sample into oxygen. So here air sample passes through ozone scrubber and comes in the absorption cell. Again UV light passes through it and detected by UV detector. Now two cycles are discussed. One is direct path, one is through ozone scrubber path for 10 seconds. So I lambda for first cycle, I lambda which is measured by UV detector will be equal to I0 lambda exponential minus 0 to L sigma for ozone at wavelength lambda density of ozone plus other absorbing scattering species present in that particular air parcel at this wavelength lambda. Correct? For the next 10 cycle, we know that number density of ozone is 0 and intensity will also change. So I dash lambda will be measured in the next cycle and it will be equal to I0 lambda exponential minus 0 to L sigma dash lambda number density of other species. So this will be all the interfering species which will contribute for the calculation of I dash. And I lambda will be absorbed by ozone as well as other interfering species. Now, if we take the ratio of these two, I by I dash, it will be equal to exponential minus 0 to L sigma ozone, number density of ozone dl. Effect of this interfering species will be cancelled out. Now for first 10 seconds our UV detector is measuring I. For next 10 seconds it is measuring I dash, right? So these two quantities are known. Sigma ozone for that particular wavelength is already known from the previous experiments. It is already a known quantity. So only unknown in this equation is number density of ozone, right? So using this a particular Beer-Lambert law principle, we can calculate number density of ozone in the ambient air parcel, right? Now another instrument, there are other instruments, similar instruments are also present. CO analyzer also based on Beer-Lambert law, and it absorbs 4.7 micrometer. Here this instrument is based on 254 nanometer absorption. NO2 is based on chemiluminescence method, and in this chemical equation takes place and then photons are calculated for getting the number density of NO and NO2. And sulfur dioxide analyzer is based on the fluorescence method. Now we will go for the satellite measurement. So satellite remote sensing of trace gases is again depends on the absorption by the atmospheric gases present in our atmosphere. Two type of radiation is received by satellite. One is reflected solar radiation and second is emitted terrestrial radiation. Solar reflected radiation is the solar energy which is reflected from the surface of the earth, and emitted radiation is from the surface of the earth as well as from different layers of the atmosphere. Okay, and we know the distinct absorption spectra of each trace gas, correct? Like we already know that CO absorbs 4.7 micrometer. We know that ozone absorbs 9.6 micrometer. So we know what is the absorption band of different gases. Here example is shown. It is terrestrial radiation spectrum measured from a satellite. Terrestrial means earth. So earth radiation spectrum measured from a satellite. And here the dotted line shows the black body curves at different temperature, and this solid line shows the radiation spectrum of our earth. Y-axis shows radiance and x-axis shows wavelength and wave number. So here you can see at 9.6 micrometer ozone is absorbing. So you can see a dip because of the absorption of photons at 9.6 micrometer by ozone. So from our previous knowledge, we know that different gases absorb different wavelengths in the UV visible and infrared range, and that property is used for their calculation. So suppose if we are making measurement at close to 9.6 micrometer, we know that in the atmosphere ozone must be absorbing that particular wavelength. So this information is already there with us, and this information is used for the retrieval of gases in the atmosphere. So when we see the reflected radiation from the sun, then this light travels through the atmosphere, reaches to the ground, then it is reflected from the surface of the earth towards the satellite. So it is passing through the atmosphere twice, and so solar radiation, when solar radiation is used for retrieval of gases, it provides columnar information, means from surface to top of the atmosphere total content of particular gas. And what is the measuring principle? In the previous slide we have seen the absorption, absorption cell and ozone scrubber. So, but in the atmosphere, what we cannot do, we cannot kill ozone in the atmosphere for this calculation. So what we do another thing. We make measurement at different wavelengths. At some wavelengths which are not strongly absorbed by gas, and some wavelengths which are very strongly absorbed by gas. So if you make comparison for those wavelengths which are strongly absorbed and which are not strongly absorbed, then the ratio will again give you concentration of species, target species or species absorption species. So using this principle, we can get total column content of different gases present in our atmosphere, which are absorbing in the UV visible range. So we will see what all are these gases and what all are the instruments. So two instruments at present which are working: ozone monitoring instrument and tropospheric ozone monitoring instrument. It is commonly known as OMI and this is known as TROPOMI. So these two instruments provide total and tropospheric column of NO2, ozone and sulfur dioxide total column content or tropospheric column content. And this tropospheric ozone monitoring instrument, which is an advanced version of OMI, it is called TROPOMI, and it also makes measurement for total column CO. So it provides, these two instruments provide total and tropospheric column of these three gases are given by OMI, and all four gases are given by TROPOMI. And TROPOMI is best observation available for these pollutants, but TROPOMI gives only column information, not the vertical distribution. So now we will compare OMI and TROPOMI observations. OMI is on board Aura satellite and TROPOMI is on Sentinel-5P, and OMI observations are available from July 2004 and TROPOMI observations are available from October 2017. The structure of the instrument is similar. Both are nadir viewing imaging spectrometer, and this OMI measures in UV and visible range from 264 to 504 nanometer, and TROPOMI measures UV visible as well as NIR and SWIR, near infrared and short wave infrared radiation also, and it ranges from 270 nanometer to 2.3 micrometer. The spectral resolution of OMI is 0.42 to 0.63 nanometer and spectral resolution of TROPOMI is 0.55 nanometer. This is the nadir viewing, spatial resolution 13 cross 24 kilometer square, and the spatial resolution, if you see for TROPOMI, it is much better, 7 into 3.5 kilometer square. And in some bands, the resolution is slightly poor, but still 7 kilometer by 7 kilometer information is also more than sufficient to see the pollutant gases in the atmosphere from space. And both the instruments provide global coverage daily with swath 2,600 kilometer. Now, in this plot, you can see the spatial distribution of tropospheric column NO2 and from OMI as well as from TROPOMI. So you see the spatial resolution of OMI and TROPOMI. The spatial resolution of OMI is poor, so you can roughly say that this is the pollution hotspot, but here how clearly you can see the pollution hotspots and what is the value of pollutants over different points. So TROPOMI observations are very important, and TROPOMI observations are best at present for total column content calculation. But TROPOMI or OMI or using the reflected radiation, we cannot give vertical profile of pollutant gases. Vertical profile of pollutant gases can only be calculated by emitted radiation from our terrestrial system, from surface as well as from different layers of the atmosphere. We all know that every body having temperature greater than 0 Kelvin emits radiation according to Planck's law, and this is the Planck's function B nu T, which is a function, the total radiation emitted is a function of a wavelength or frequency and temperature of the body. So each body, even our surface of the earth and different layers of the atmosphere, will emit radiation for different wavelengths according to their own temperature. So suppose our earth is emitting at one particular wavelength lambda or frequency nu, suppose our earth is emitting radiation, then that radiation will be absorbed by overhead atmosphere, because absorbing species are present in our atmosphere. Similarly, according to the temperature of different layers, every layer will also emit radiation in vertical direction, and that will again be absorbed by the overhead atmosphere, right? So if we make one particular measurement, suppose for example 9.6 micrometer, then 9.6 micrometer wave radiation which is received by satellite will be coming from surface as well as from different layers of the atmosphere, correct? Suppose spectral radiance received by the satellite at frequency nu is given by L nu, then it will be equal to B nu Ts, where it is the surface term. B nu Ts is the Planck function for surface temperature at surface temperature, that is Ts. Ts is the surface temperature, nu is the frequency, and B nu Ts is the Planck function. Now that radiation will not reach completely because there are absorbing gas. So we have to multiply it with transmittance, right? So transmittance at particular wavelength or frequency is given here, tau, multiply tau, which is from surface, that is altitude 0, to top of the atmosphere, that is infinity. From surface to top of the atmosphere, transmittance is multiplied in Planck function of the surface of the Planck's function calculated at temperature Ts. So this will be the upwelling radiance from surface of the earth. And this is surface temperature, surface term, and then there is atmospheric emission term. So we know that there are several layers in the atmosphere which are emitting. So we have to integrate from surface to top of the atmosphere, contribution from different layers. And this is the Planck function, and according to temperature of different layers. So it is changing from 0 to infinity, Z is changing, and B nu Tz is the temperature of one particular layer at altitude Z, and this is rate of change of transmittance with altitude. It is called weighting function, and transmittance from that particular layer to top of the atmosphere, right? And it is the rate of change with altitude or pressure, and it is called weighting function. And this is the function which it decides that we can get the information about the vertical distribution of pollutant gases in the atmosphere. How? That we will see in the next slide. So here, suppose this is an absorption band of one particular gas. Recall here, we can see this is absorption band of ozone, right? So it is decreasing the transmittance. So here you can see that if the wavelength λ3 is very strongly absorbed by the absorbing gas, then the transmittance will be very, very low. Transmitted energy will be very, very low with respect to incident energy, and accordingly transmittance will be very small. And if wavelengths are not strongly absorbed, like λ1, which is not strongly absorbed, then transmittance will be close to 1, right? So here, for example, 3 wavelengths are chosen in one absorption band. Here it is an absorption band by an absorbing gas, and here 3 wavelengths are chosen, λ1, λ2 and λ3. Now consider λ1. λ1 is very poorly absorbed, right? The gas is not very strongly absorbing this particular wavelength. Absorption cross section is not very high for this wavelength. So what will happen in the atmosphere when it is emitted from the surface of the earth? Very small amount will be absorbed by the overlying atmosphere, and transmittance will quickly increase with increasing altitude, and very quickly in the atmosphere it will achieve value 1. It is the variation of transmittance with altitude or pressure. Okay. So here you can see it is increasing very rapidly, and very soon in the atmosphere it will reach value 1. Now consider λ3. λ3 is very strongly absorbed by our atmosphere, right? So if we make measurement and λ3, so whatever emission is emitted from the surface, the overlying atmosphere will be immediately absorbing those photons. So transmittance will be 0, because number density is maximum near surface because of the gravitational pull. So number density is maximum near surface and exponentially decaying with increasing altitude. So number density is maximum near surface, absorber number density is maximum near surface, and it absorbs all the photons emitted from the surface of the earth, and it doesn't allow any photon to leave the atmosphere. Now this layer again according to its own temperature will emit some radiation, will be absorbed. Then this layer will also emit and it again will be absorbed and so on. So process will go on up to certain altitude. But absorber number density is continuously thinning. Number density is decreasing with increasing altitude. So beyond one layer, the absorber number density will be so low that it will allow some radiation to pass through it. Now transmittance will start increasing with increasing altitude. It will increase, and with increasing altitude it will reach maximum at 1. So we can see rate of change of transmittance for lambda 1, lambda 2 and lambda 3. It is change of transmittance. Now we will see rate of change of transmittance with pressure. So first consider lambda 1. If you consider lambda 1 from surface, if you go just very little high in the atmosphere, there is rapid change in the transmittance. So rate of change of transmittance is maximum near surface and it is decreasing with increasing altitude, and it is 0 beyond this. When the transmittance is 1, the rate of change will be 0. Right? And for consider lambda 3. Lambda 3, from here to this altitude, the transmittance is 0. So transmittance is not changing. So the rate of change of transmittance will also be 0 till this altitude, and beyond that it will again increase. It will reach some maximum somewhere over here, and then it will again decrease. Right? So these are called weighting function because they weight the atmospheric layer contribution. Now consider that if we are making measurement at lambda 3 by our satellite, then lambda 3, this weighting function in the previous equation, here this equation, if we are making measurement at lambda 3, it will be multiplying only between this altitude to this altitude. So it will giving the contribution only from this particular layer. If we consider lambda 1, it will be giving maximum contribution from surface only. And if we are considering lambda 2, it will be giving contribution from one intermediate level. So if we are carefully making measurement, we are considering wavelengths in the absorption band of absorbing gas, and we are making measurement at different wavelengths in the atmosphere, what will happen? We will be able to get the vertical profile, because lambda 1 will give you near surface value, lambda 2 will give you information about the middle atmosphere, lambda 3 will give you information about the upper atmosphere. So it is basically weighting function. This is rate of change of tau with pressure, or rate of change of tau with altitude. This is called weighting function because it weights this term in this equation. So contribution will come from one specific layer only, and that information, this particular principle is used for getting the vertical profile of those gases which have absorption band in the infrared radiation in which our earth and atmosphere system emits radiation. So for these CO and ozone, these two gases have infrared channels. CO absorbs at 4.6 micrometer and ozone absorbs at 9.6 micrometer. These are the wavelengths used for the calculation of their vertical profile from space. And these are the working instrument. I have only included working instrument. So these are the working instrument: MOPIT, measurement of pollution in the troposphere. It is an instrument on board TERRA spacecraft. Horizontal coverage is 22 km by 22 km nadir footprint with 612 km cross-track scanning. And global coverage it provides in 3 days, and overpass time is 10:30 in morning and evening. The second instrument is atmospheric infrared sounder, and it is on board ECWA spacecraft. Horizontal coverage is 1650 km with horizontal resolution of 14 km by 14 km at nadir. It provides daily global coverage, and it provides CO and ozone both. MOPIT provides only CO profile. IIRS provides CO and ozone, both these gases. IASI infrared atmospheric sounding interferometer. It is on board METOP spacecraft, and its horizontal coverage is 22 kilometer, 100 kilometer, and with a spatial resolution of 12 kilometer by 12 kilometer. It also provides global coverage. So these three instruments provide vertical distribution of carbon monoxide and ozone from space using emissive radiation, earth terrestrial emitted radiation. Now we will understand application of satellite observation of gaseous air pollutants. So satellite observations can be used for identification of hot spots, because suppose you can ask why we require satellite data. We can make measurement from the in situ observations, but in situ observations are very costly. Each instrument which I showed in the previous slide costs around 5 lakh to 12 lakh rupees, and then calibration system and other supporting system is also required for that trace gas laboratory or air pollution laboratory. So it is very costly business, and the concentration of pollutant gases changes rapidly in the spatial domain. So we cannot make very dense network because of the cost limitation, or as well as we cannot make very dense network because we can make 200, 300 observational location in India, but we cannot go very high number of observations. But satellite can fulfill this gap. Satellite can give, now satellite is giving at 7 kilometer by 7 kilometer spatial resolution data. So satellite data can fulfill this gap. Other thing is that if you make measurement by thermometer, 2 thermometer you take and you try to measure your temperature, 2 thermometer will not give you same value. A slight difference will be there. So if you are making measurement by using the same instrument, that there is also added benefit. And satellite is same over India, over China, over Europe. And if you are making measurement, you are taking satellite measurement, you can compare the pollution level over their location or our location, right? So here, global tropospheric column NO2 absorbed by tropomi is shown. We can identify emission hotspots. Here you can see Chinese emission, you can see European emission, France, Italy, Germany, you can see New York emission, Washington emission. You can see emission hotspots from satellite if your satellite data has fine spatial resolution. You can very clearly see over India, this is the location of Lahore, then this is location of Delhi, and here you can see some small locations, hotspot locations. These are basically thermal power plant emission. And it is NO2 tropospheric column in micromole per meter square. Now we can use the spatial, we can study the spatial distribution as well as temporal distribution using satellite data. As we know that satellite is continuously rotating around our Earth, and it is giving us repeated data in spatial domain also and in temporal domain also. So here example is shown taken from Girach and Nair 2014. This is the mean column CO, molecule per centimeter square over the Indian region, and it is the gridded data at 1 degree by 1 degree, and we can see the variation. And they have chosen different region over Indian region, like arid India, Western India, North Arabian Sea, South Arabian Sea, and so on. Several locations they have, so several boxes they have chosen, and over these boxes they have averaged the value and shown in the right hand side plot. I have taken only 3 plots from their study: arid India, Western India, and North Arabian Sea. So here you can see the variation of satellite data. Monthly variation of satellite data at 900 hectopascal for arid India, Western India, and Northern Arabian Sea, and this is shown by black curve at 900 HPA, and at blue curve shows the variation of CO at 200 HPA. Vertical profile is available from MOPIT. Remember, that is why we can get lower atmospheric and upper atmospheric value of CO. And also mean column concentration of CO in molecule per centimeter square, which is shown by the red curve. So if you have understanding about the atmospheric boundary layer dynamics and wind pattern over the Indian region, you can understand why we are getting the specific variation in the atmosphere like this. So we are getting high value near surface, we are getting high value during winter time and low value during summer time. It is also contributed from the Indian summer monsoon and also atmospheric boundary layer dynamics. Now, using satellite data, we can study extreme pollution episodes. Here in the background, you can see spatial distribution of carbon monoxide over the Indonesian region, and there is very high pollution plume you can see in the background picture. It is taken from MOPID data, measurement of pollution in the troposphere, and here you can see the variation in the concentration of carbon monoxide over this region, bounded by this box, this latitude and this longitude. Over this region we have made a box, averaged the MOPID data which is available from 2000 onwards. So here you can see the variation, the decadal variation is shown at 500 HPA, 400 HPA and 300 HPA, that is free troposphere, right? So here you can see in 10 decade you can identify some abnormal events also when the values are very, very high. And then we can investigate why the value is so high over that location. Here you can see fire hotspots by red lines, and these are the fire events identified by satellite over this region. And here the blue curve shows the columnar CO over this box. This is a box made by these latitude and longitude. So over this region we made a box. Over this region we calculated the total fire hotspots, means locations where fire is ongoing during this period. So you can see during 2006 it is calculated and found that in October, November, when the values are very, very high in the atmosphere, that time intense biomass burning was ongoing over the Indonesian region. So we can identify the extreme pollution episodes using satellite data. Then long range transport, we can calculate the concentration at different days, and we can see that how the pollution plume is traveling in the atmosphere. Here you can see MOPID CO. Here you can see MOPID CO at 600 millibar. It is taken from visible Earth NASA images, and within 5 days you can see a Chinese pollution plume traveling across the Pacific Ocean and reaching the Northern American region. Similarly, here you can see OMI, ozone monitoring instrument, SO2 column in Dobson unit. And here you can see that there is a Dalafilla volcano in the Ethiopia region, and it erupted and emitted a lot of sulfur dioxide in the atmosphere. It traveled through this path. It reached over the Indo-Gangetic belt. It traveled through the Indo-Gangetic belt and then it dissipated. So using satellite data, we can track the pollution plume for long distances. We can see long range transport of pollution plume. See, it is 4 November, 5 November, 6 November and 7 November. Within 4 days, this pollution plume traveled from this location to our Indian region. So we can identify the track of pollution plume even for longer distance. Satellite data is available for decades also. So if the data is available for long time, we can calculate the long-term trend. We can see whether pollution level is increasing or decreasing or constant over one location. For example, here tropospheric NO2 trend is calculated over South Asia. It is taken from Huck et al. 2015. And it is area averaged annual distribution of OMI NO2 over the South Asian region during 2005 to 14, and it shows clearly increasing trend over this region during 2005 to 2014. This is the y is equal to mx plus c fit, and it shows a slope is equal to itna, and this is the intercept, and this is r square. So we can calculate long-term trend. If we have access of satellite data, we can calculate long-term trend of pollutants. Now, this is a very specific event, the COVID-19 induced lockdown, which was implemented on 25th March over the Indian region, right? And here you can see that after lockdown implementation, this is the picture of OMI NO2 during 2020, during 25th March to 19 April. And you can see the distribution of OMI NO2 tropospheric column over the Indian region. Now, we have gone back and calculated the average of OMI NO2 during the same period for previous years, during 2017 to 19. 3-year average is shown in this picture. So you can see very high pollution level in previous years. We can see Lahore, we can see Delhi, we can see Mumbai from the space. But in 2020, you can see only 4 emission hotspots in the Indian region, and these are the location of thermal power plants. These are the location of thermal power plants having capacity more than 2000 megawatt. And this is the NO2 change, this plot minus this plot. So this shows the change, means reduction in NO2 throughout the Indian region, except somewhere or western area where the transport is bringing the polluted air from western direction. The same event is studied using TROPOMI data, which is finer resolution data. So here you can see location of Lahore, New Delhi, Mumbai, Bangalore, and Hyderabad during 2019 during April 1 to 6, 2019 and during 2020. So you can see cyan color throughout the Indian region, but here you can see dark blue color, and because of the reduced emission, because of the lockdown. Because of lockdown, anthropogenic emission suddenly stopped, but thermal power plants were working, so we can see their emission from the space. Some applications using chemistry transport model. Chemistry, basically satellite can give you 3-dimensional picture of polluted gases, but satellite cannot give you any information about atmospheric processes responsible for pollution episodes. For that, we use chemistry transport model. Chemistry transport models simulate a spatial distribution, 3-dimensional distribution of chemical species by mathematical calculation, by considering anthropogenic biomass burning and natural emission, by considering advection and convection process over different grid boxes. So here you can see the grid boxes over the global region, and these are the grid boxes, and each box, within each box, continuity equation for different species are solved, which basically shows the change in the concentration of pollutants within that box due to advection, convection, and gas chemistry. So a specified time period is considered, suppose 20 minutes, and and initial conditions are considered. Initial condition means globally 3-dimensional value of all the species at time t is equal to 0, the starting point. After that, we consider the emissions from the surface, we consider the effect of advection, we consider the effect of convection and gas chemistry. So here you can see for first time interval, for first 20 minutes, the advection is allowed. We've been allowed to change the number density within the grid cells. After that, advection will stop after 20 minutes, and the output will be considered as input for the next process, that is convection. Now convection will be allowed to change the concentration within each grid cell. After that, you will get another output, and after that advection or convection will be stopped, and only gas chemistry will change the concentration in each grid. So it is seeing the change because of advection, convection, and gas chemistry theoretically. Mathematically, we are calculating the 3-dimensional distribution of chemical species like CO, NO2, ozone, all these gases, theoretically calculating, not getting from any observation. And then you will get, after 3 processes, you will get an output. Suppose we have considered time interval 20 minutes. So 20 minutes for advection, 20 minutes for convection, and 20 minutes for gas chemistry, and you will get one output. That output will be input for other. So after 3 time intervals, you will get one significant, physically meaningful output. So using this method, using the chemistry transport models, we can simulate, mathematically calculate the global distribution, 3-dimensional distribution of different chemical species. So same thing we will get from the satellite data, and same thing we can calculate using chemistry transport model. But it is mathematical calculation, maybe there may be some error. So validation is very important. So a very important application of satellite data is validation of model simulations. So if model is, here you can see 2 plots. This is MOPIT observation at 500 millibar for that Indonesia event. And here it is model simulated event. Model will not be able to simulate exact values, but it should be able to reproduce the observed features. If model is able to reproduce the observed features, model is considered reliable. And then model can be used for understanding the pollution episodes. So model is a theoretical calculation. We can play with the emissions in the model simulation. We can do the calculation with and without emissions. So here we, after validating the model performance, after getting confidence on the model performance, we have run model twice, one with emission and one without emission. And using this, we can calculate at each pressure level the change in the carbon monoxide value from surface to 100 hectopascal. So model can give you additional information, but validation of model is very, very important. Then we can develop the satellite constraint emissions inventory using satellite based observation. Suppose your model values are not matching with your satellite observation, then satellite data can be considered as reference, and you can fine tune the model inputs by considering satellite data as reference. Here WRF model is run for calculation of tropospheric column NO2, and that was not matching with the satellite observation OMI. Here you can see the difference between the two. So what we did, we corrected emissions using tropospheric column calculated by model, input NOx emission used in the model, and OMI tropospheric column. Iteratively we use this. So initial emission, initial calculated tropospheric column, and OMI observed tropospheric column NO2 is used in this equation to calculate improved emission. Now we fed this improved emission in model simulation. Again we got total column from model, and again we got the new emissions. So by iterative process, we can reduce the difference between model and observation. And when the error, here you can see after 7 efforts, this is the spatial distribution simulated by WRF, and this is the difference between observation and model. So satellite data can be used for correcting the model satellite, this atmospheric model inputs. It can be used for calibration of model. Now if you are interested in using satellite data, you can use Giovanni portal. Giovanni is NASA portal, and you will type Giovanni in Google search bar, then you will get this first link, and click on this link, then this page will be open. Now here you will see observation disciplines. So click on observations and atmospheric chemistry. So you will click on observations and atmospheric chemistry. You will get different data, carbon, ozone, NO2, ozone, and CO. You will get data from different platforms. So here you can choose one of the pollutants. Like here I have chosen NO2. So you can see what are the data available. It is OMI data from in molecules per centimeter square. It is daily resolution data at spatial resolution at 0.25 degree cross 0.25 degree, and begin and end date is also given. So if you have this data, you have to select this data from here, and then you can generate time averaged map or time series at area averaged time series map, time series variation. So you have to click on this drop down window, and you can select time averaged map, or you can select time series area averaged. There are other options which you can explore. Then here select date range. From here to here you can select some date range. Suppose you are using time averaged map, so you will get, suppose I want to average it for 10 days. So it is given from 1st October to 10th of October. So during this period, whatever observations are available, that will be averaged. And when you will click on this symbol, it will this window will be open. Now click on this box and drag down it, and you will be able to select any area over the this region. So you can click on the plot data, and you will get a spatial distribution. And using this spatial distribution, you can see the pollution hotspots. Also, you can download from here. You can download the data, net CDF file, PNG file, or GeoTIFF file for this plot. So if you are interested in assessing the criteria air pollutants data, you can use this portal. Thank you.